And now using this model, I also attempted to simulate an El Nino event in a very, very simplified form. And again, I don't give you much background, just a little bit of background. Just a little bit. El Nino events are created along the equator in the Pacific region. It essentially starts with a wind disturbance over the western equatorial Pacific Ocean and a wave, particular wave in the ocean that propagates eastward along the equator. It's so-called equatorial Kelvin. So that is sort of the key ingredient. And this is what shows the onset of an El Nino event from satellite observations of the cloud pattern. You can see that normally we have winds from the east, easterly winds, trade winds, so-called trade winds over the equator. But here you can see a wind burst coming from the west. And what it does, it actually produces a cyclone pair north and south of the. This is what you try to do in a computer simulation. And there's a little bit more that you need. All right. Okay, so El Nino events are associated with so-called equatorial Kelvin waves that can only propagate to the east, the west. And I urge you just to read a little bit about them. So what do we do now in this simulation? Okay. So we use the three-dimensional model, but only to a water depth of 250. Relatively coarse resolution, because I told you it takes a long time to simulate. Why do we use only shallow? Because the deeper you make your model domain, the smaller has to be the time step. This is called the CFL condition, stability condition. Laurent Friedrich Levy. And this is why it doesn't make sense to make it a little bit. And it's only a two-layer configuration. But anyway, so what the key is actually how do you express the Coriolis force? Because the Coriolis force, the Coriolis parameter, disappears at the equator. North of the equator, you have a positive Coriolis parameter. South, you have it negative. And this is what the way you represent that is called the beta plane approximation. Here is shown in the top formula. You make the f as a function of the distance from the equator, whereby the distance turns negative in the southern hemisphere, like shown here in this sketch. And then the model is driven by having a westerly wind burst. And this is the structure of the westerly wind burst. And it's only created here on the western part of the. And this is what creates the equatorial Kelvin. And let's have a look at it. This is a simulation. The wind burst, and you can see the blue pattern, the wave that propagates along the equator. And then there's actually similar waves which propagate away from the equator, which are called coastal Kelvin waves. Right? 50 days of simulation. I go back and do it again. Let's see. This is an El Nino, or the ingredient of an El Nino. You can also see these events if you look at sea surface temperature observations from satellites. Because these waves do is actually they lead to a relatively warmer sea surface. And you can track these events by looking at sea surface temperature anomalies. This is shown on the next slide. Not yet. So these are the snapshots from the model simulation I just showed you, and on the next slide you show signature of sea surface temperature anomalies, variations, and you see them here developing for the western parts of the Pacific Ocean and propagating over to the. So that's pretty much it.